So let's look at lime soda ash softening. What we will look at in this unit is we'll first look at hardness. I have a hardness and alkalinity review that's on YouTube that I posted basically for 480, but it applies to what we are doing here. Some of what is on that is we will repeat here, but it's also a good review, so that if you don't remember hardness from ENE 280, it's a good place to go and review. We'll look at lime soda ash softening as a process. We'll look at process configurations and design criteria, some operation maintenance, and then we'll look at stabilization and talk about the importance of stabilizing water to ensure that the water that's provided to consumers is safe and potable. We'll talk about what those problems are at that point in time. So let's look first at hardness. Hardness is a term that's used to characterize the ability of the water to cause soap scum. Those of you living in res halls may find that the water is extremely hard. Where it's extremely hard, it's predominantly due to the presence of calcium and magnesium. And these are naturally occurring minerals. They're present in the aquifer materials, but they just slowly dissolve into the groundwater. And the problem with these is they increase the amount of soap that's needed. They cause scaling on the pipe, and what you're seeing in the side of this pipe here. So this is the scale that we talk of, predominantly in this case, calcium carbonate. And these also precipitate on valves, and they cause the valves to stick. They leave stains on plumbing fixtures. They also can precipitate in a hot water heater and then cause a poor efficiency of heat transfer in the hot water heater, and that increases your energy bill, electric bills, or gas if you're using gas. So as I mentioned, these are naturally occurring minerals. What happens is there's microbial activity that produces CO2. And that CO2 reacts, so we produce CO2, it reacts with water, and it forms carbonic acid. And that lowers the pH of groundwater. So typically groundwaters have a pH often around 6 to 7 to 6.5 in that region, and that's because of the presence of carbonic acid. So what happens is limestone minerals contain calcium, magnesium, react with the carbonic acid to release calcium and magnesium, and you also have, in this case, this is shown as bicarbonate. When we talk about hard water, we typically use the terms of versus soft versus hard. Okay? So extremely soft water is water that has a hardness 0 to 50 milligrams per liter is calcium carbonate. In some of the residence halls on campus, there are point of entry ion exchange units or reverse osmosis units. These are softening units. And in that case, the water in the res halls is extremely soft. Unless they're blending, it's typically extremely soft. What we are looking to produce is water that typically has a hardness of about 100 to typically about 120 milligrams per liter, and this is as calcium carbonate. We'll talk about that in a bit. This provides some protection to the pipe. So if this is the end our pipe, so this is the inside of the pipe. what we get is some calcium carbonate that precipitates along the inside of the pipe. We don't want the extent of scale formation that you saw in that previous picture, but providing some precipitate on the inside of the pipe protects the pipe from basically dissolution. In working with ENE 480, I actually went into the research complex this weekend to obtain some samples and to test the water there. And in one of the taps where water had been sitting for a long period of time, the water that came out of the tap was actually a gray color. It actually smelled of hydrogen sulfide. It had that rotten egg smell. So what we probably were getting in that pipe was sulfate reduction to sulfide and dissolution of the iron pipe. So what I was actually seeing was particles of iron. I've just sent the sample in to chemistry to be analyzed, so it'll be interesting to see what the results are there. I'll let you know. So when we talk about hardness, we talk about carbonate hardness and non-carbonate hardness. Carbonate hardness is often also called temporary hardness. And that's because if we heat the water, we'll remove the hardness, okay, or at least reduce the hardness. So if you were to measure hardness of your tap water, you would have the hardness of your tap water, but then if you measured the hardness of the hot water, it should be lower than the cold water tap, and that's because some of that temporary hardness has actually precipitated in the hot water heater. So what we typically do, okay, is that they precipitate as a calcium carbonate, and that's because calcium carbonate is actually more insoluble at higher temperature. So this is the calcium and magnesium that's associated with either bicarbonate or carbonate. And the carbonate hardness is equal to either the total hardness or the total alkalinity, whichever is less. And we'll go through an example, and hopefully that will make more sense when we actually look at an example. Non-carbonate hardness is called permanent hardness, and that's because it's not removed when the water is heated. It's much more expensive to remove non-carbonate hardness. So if we can design a process to remove the carbonate hardness, but leave the non-carbonate hardness in the water, it's actually beneficial from a cost perspective. So the non-carbonate hardness is equal to the total hardness minus the non-carbonate hardness. And if the alkalinity is greater than or equal to the total hardness, then the non-carbonate hardness is 0. So it's that hardness that's associated with ions other than bicarbonate or carbonate. Hardness is reported in units of either milligrams per liter as calcium carbonate, parts per million as calcium carbonate. You will sometimes see it reported as grains per gallon. And to convert from grains per gallon to milligrams per liter, simply multiply by 17.1, or it can be reported in equivalents per liter or milliequivalents per liter. Typically, in the water industry, you will see it reported as milligrams per liter as calcium carbonate. So the objectives of lime soda ash softening, and it's really true for all softening processes. So we want to reduce the concentration of calcium and magnesium. We want to produce water that's at an acceptable pH. And if necessary, we want to reduce the concentration of other metals to meet drinking water standards. So for example, in the thumb area, arsenic levels in the groundwater are often quite high. So they're using lime soda ash softening. they can also achieve arsenic removal in some cases and be able to meet the drinking water standards for arsenic using lime soda ash softening. Now, lime soda ash softening is limited by the solubility of these minerals. So at 20 degrees C, calcium bicarbonate has a solubility of about 170 grams per liter. On the other hand, calcium bicarbonate has a solubility of about 6 milligrams per liter. Okay, so this is 170 grams per liter. This is 6.2 milligrams per liter. So you can see this is actually plotted on a log scale here. And if we start at a pH of 7 here, and we increase the pH, let's say to 11, we have a decrease from about 5 times 10 to the minus 3, and this is in moles per liter, down to about 9 times 10 to the minus 4. So about an order of magnitude decrease in the concentration from a pH of 8 to 11. The reason this is the case is, if you look at this plot here, if we're at a pH of 8, then bicarbonate predominates. If we raise the pH to 11, then the concentration of bicarbonate decreases and the concentration of carbonate, so you can see at pH 8, the concentration of bicarbonate is on the order of 10 to the minus 6. Sorry, the concentration of carbonate is on the order of 10 to the minus 6. But if we raise the pH to 11, then we have a concentration of around 10 to the minus 3. On the other hand here, if we start at pH 8, we're at about 10 to the minus 3. That's the log of the concentration, and we lower it to about 10 to the minus 4. So we get about 1 log or 1 order of magnitude decrease. So what we want to do is we want to produce calcium carbonate because the solubility is much less than that of bicarbonate. So in order to do that, we want to raise the pH. Basically, that's the goal. Magnesium bicarbonate, so if we start at a pH somewhere around neutral pH, where bicarbonate predominates, the solubility of magnesium is 37 grams per liter. However, if we raise the pH to where carbonate predominates, we can reduce the solubility by about 3 orders of magnitude. However, if we can precipitate that magnesium as magnesium hydroxide instead of magnesium carbonate, the solubility decreases by about another 2 orders of magnitude. So starting at a pH of, let's say, around 6 to 7, where bicarbonate predominates, we have a solubility of magnesium bicarbonate of about 37 grams per liter. But if we can raise the pH to where we form magnesium hydroxide precipitate, the solubility drops to about 10 to the minus 2 grams per liter. So we're in the milligram per liter range. It's about 10 milligrams per liter. So this is actually about 10 milligrams per liter. And you'll see this, we'll talk about this in just a little bit in terms of process limitations. So we can also achieve removal, as I mentioned, of other species. So we can remove iron and manganese. And it's interesting with MSU. MSU has softening as I mentioned, as point of entry systems in a number of the residence halls. When they were debating whether to build a new water treatment plant, they could have softened the water at the plant, and that would have eliminated all of these point of entry systems. Or they could have just achieved iron and manganese removal. For whatever reasons, and most likely cost, it was chosen that they would simply do iron and manganese and not to soften the water, which means that the res halls still will soften water. It will also remove naturally occurring organic matter, essentially a precipitation reaction, that the organic matter gets incorporated into the precipitate and settles out with the precipitate. And the same is true with turbidity. It also can potentially remove other metals. So for instance, if we look at zinc and we start out at a pH of 7, so we start here, and we raise the pH to about 10, we decrease the solubility from about 100 milligrams per liter down to 0.1. But notice, as we raise the pH, we actually increase the solubility. If we go up to 11, we're at a solubility of 1. So we can get about a 99% removal, actually, ideally, in this situation. So it doesn't, solubility does increase, but you do get some removal. Nickel is here. You can see nickel. You get very good removal if there was nickel in the source water. Same with cadmium. Not true for lead. Lead is a challenge. Copper, you would get removal. Chromium, notice the solubility of chromium has a minimum about 7.5 and then actually increases significantly beyond that. So chromium, we could not remove with lime soda, so not to any appreciable extent could we remove it with lime softening. So these are the reactions that occur. As I mentioned, it's a significant amount of chemistry. But if you simply think about it as balancing an algebraic reaction, hopefully it becomes a little more straightforward and less challenging. So as I mentioned, groundwaters will often contain CO2. So the first reaction that we need to do is to neutralize that CO2. We get no, notice here, we get no hardness removal. We're simply increasing the pH. So the goal with this first reaction here is to neutralize the CO2. So we add lime. This is actually shown as hydrated lime. Hydrated lime, what we typically add is quicklime, and that we hydrate at the plant, and that produces calcium hydroxide, or hydrated lime. So we precipitate the CO2 and hydrated lime as calcium carbonate. So we're producing a sludge. So I've shown the sludge that we produce, the solid residual, in green. I've shown the chemicals we're adding in blue and the reactant in red. So we're removing calcium. The second reaction is a precipitation of carbonate hardness due to calcium. So it's that calcium associated with bicarbonate. We add lime, and notice here, we're actually adding calcium to remove calcium. And it's a 1-to-1 stoichiometry. So for every 1 mole of calcium we remove, we need 1 mole of lime. But we produce 2 moles of sludge. So we produce a significant amount of sludge from this reaction. Second reaction is the precipitation of carbonate hardness due to magnesium. So this is the magnesium that's associated with bicarbonate. For every 1 mole of magnesium, we need 2 moles of lime, and we will produce magnesium hydroxide and calcium carbonate. So we produce 1 mole of magnesium hydroxide, 2 moles of calcium carbonate. In order to achieve this reaction, we need to increase the pH to 11.3. So we need a high pH. Here we're typically operating at about 10.5. So we need to increase that pH significantly above what we need to remove the carbonate hardness due to calcium. Then we have the reactions for the non-carbonate hardness. Here we have to add soda ash. Sodium carbonate is referred to as soda ash. So for every 1 mole of calcium we remove, we need 1 mole of soda ash. We will produce 1 mole of lime. And notice we're also adding sodium ions. To remove the non-carbonate hardness due to magnesium, we need lime, we need soda ash, we will produce magnesium hydroxide, we also produce calcium carbonate sludge, and we add more sodium. Basically, it's more expensive to remove non-carbonate hardness than it is to remove carbonate hardness. So if we can avoid removing the non-carbonate hardness, we will. If we can avoid removing the magnesium but still produce desirable quality water, we will avoid removing magnesium. Now there are process limitations. As I mentioned, the solubility. I showed you the solubility of calcium and magnesium. So some hardness ions will remain in solution. That is not true when we talk about ion exchange or reverse osmosis, or to a much lesser extent. But with lime soda ash softening, your solubility, because of these limitations, you will typically produce a water that has about 40 milligrams per liter as calcium carbonate. And that's because, one, the solubility. The other thing is that solubility reactions are not rapid. It's unlike an acid-base reaction, which is almost instantaneous. Solubility reactions are time dependent, and there may be incomplete time for a complete reaction to occur within the flocculation basin. There's also non-ideal mixing. We've talked about that. We've talked about short-circuiting. I mentioned that, and that can result in process limitations. So what I'd like to do is go through an example. I'm going to do this example and talk about practical limits where we simply use the stoichiometry. On Friday, we'll do another example. Probably use breakout groups on Friday, break things up a little bit. But hopefully by going through this example where we're actually simply looking at the stoichiometry, it'll give you a sense of the types of reactions or the types of calculations that we need to do with these softening reactions. So we have a water. We're given the water quality, and it has 100 milligrams per liter of CO2. It has 110 milligrams per liter of calcium, 31 milligrams per liter of magnesium, and 320 milligrams per liter of bicarbonate, and these are reported as the ion. You're told that you're designing a water treatment plant with a design flow of 4 times 10 to the 4 cubic meters per day. And you're asked to determine the lime and soda ash doses to meet practical limits. This means we are looking at the stoichiometry. Look at the stoichiometry and the stoichiometry only. So I've tabulated the data here. This is the starting data. So this is the data you're given. The next thing we want to do is calculate the molecular weight, or look up the atomic weight. So I have the atomic weights or the molecular weights for these compounds. We have calcium, we have magnesium, bicarbonate, and CO2. The next thing we want to do is calculate the concentration in, and I've given it in millimoles. So for example, we have calcium 2 plus, we have a concentration of 100 milligrams per liter. We'll divide that by 40.1 milligrams per millimole. Milligrams cancel, and we have 2.74 millimoles per liter, or 2.74 millimolar. So we do the same calculations for magnesium, bicarbonate, and CO2. The next thing we need to do is determine the number of equivalents. So I've mentioned before, the number of equivalents will typically be the charge on the species. So for calcium, it's easy to see, it's 2. For magnesium, it's 2. For bicarbonate, it's 1. And what about that CO2? Okay. Remember, CO2 reacts in water to form carbonic acid. Carbonic acid can donate 2 protons, so N is equal to 2. So you'll always use a 2 for CO2. And those of you in 481, it's the same thing there. So now we can calculate the equivalent weight. So let's use CO2. We have a molecular weight of 44 milligrams per millimole. We divide that by 2 milliequivalents per millimole. Millimoles cancel, and that is 22 milligrams per milliequivalent. That is the equivalent weight of CO2. So we can do the same thing for the other species. We then want a concentration in milliequivalents per liter. So if we take that calcium, we have 110 milligrams per liter. We divide that by the equivalent weight. Milligrams cancel, and we have an equivalent weight of 5.48 milliequivalents per liter. Now we typically use milligrams per liter as calcium carbonate. So we multiply the concentration in milliequivalents per liter by 50 is right. So 50 milligrams per milliequivalent, okay, and that equals 274 milligrams per liter as calcium carbonate. So where did the 50 come from? This is the equivalent weight of calcium carbonate. The next thing we want to do is determine the total hardness, the carbonate hardness, and the non-carbonate hardness. And we're going to do that with a bar chart because it's a nice way of symbolically showing the concentrations. So let's start here. And this is 0. Not very good to scale, but this is our CO2. Typically, we'll draw the CO2 in this way, and the concentration is 227. So this is milligram, the concentration in milligrams per liter. Concentration of calcium, and we write these in the form of predominance. So calcium is of the cations, it's the highest concentration. So this is calcium. And then magnesium is here. And if we add the 128 plus the 274, this is 402. Okay? So all I've done is I've added, represents the 128. Now I can do the same for alkalinity. So my alkalinity is 262. So this is my bicarbonate. And the reason I can say that is because we said the pH was 7.3, and at a pH of 7, between 6 and 8, I can say that my alkalinity is approximately equal to my bicarbonate concentration. So I have my bicarbonate. All of the other ions here, we have to have other anions. So there are other anions that make up the charge balance. So if I look at this, my total hardness is equal to what? So the hardness, 402 exactly. It's the sum of the polyvalent cations. In this case, the only polyvalent cations you have are calcium and magnesium. So we sum those, it's 402. My carbonate hardness is equal to what? This was 262. And these are all in milligrams per liter as calcium carbonate.
Yeah.
Where does the 262 come from?
It's a smart investment.
It's that portion of your hardness that's associated with alkalinity.
Chiropractor is a lot more expensive.
Dr. Maston?
Yeah?
That part that you just highlighted, that relates to the carbonate hardness, right?
Correct.
Okay, thanks.
And if you are not muted, if you could make sure you mute yourself. So I just highlighted, okay, this is our carbonate hardness. So it's that portion of the calcium that's associated with bicarbonate. Then I'll highlight, let's pick a different color. This portion here corresponds to what? So the blue portion corresponds to, so yellow is carbonate hardness. The blue corresponds to what?
Total hardness?
The blue,
or non-carbonate hardness?
And non-carbonate hardness. So this is going to be my non-carbonate hardness. Okay. So I have 262 milligrams per liter as calcium carbonate of carbonate hardness, and I have my non-carbonate hardness is equal to 402 minus 262, or 140 milligrams per liter. So now I know my carbonate and my non-carbonate hardness. So now we need to look at how much lime we need to remove. So the first reaction is neutralization of CO2. That reaction is CO2 plus calcium hydroxide that we're adding, or we could write this in terms of calcium oxide. Reacts to form calcium carbonate, and these are the exact same reactions on the previous slide. Okay. We need to know how much CO2 we have in solution. So let's go back. We want this on a molar concentration. So we have 2.27. So we have 2.27 millimoles of CO2. So how many millimoles per liter of calcium hydroxide do we need? Exactly. 2.27 millimoles. How many millimoles per liter of calcium carbonate do we form? 2.27. The next reaction we need to think about is the carbonate hardness due to calcium. So the reaction we have is calcium. I'm just rewriting the reactions from previous page. And you do, well, there's no exams anyway, but even if there were, I wouldn't expect you to memorize these reactions. I'm just going to do ... to save time. Okay. So how much carbonate hardness do we have that's due to calcium? This is why our bar chart becomes really helpful. So let's look back. What we want to know is, what is the carbonate hardness due to calcium? So looking at your bar graph, or your bar chart, what is the carbonate hardness due to calcium? 262, exactly. Okay. So that was milligrams per liter. On a molar basis, it is 2.62 millimolar. So we need 2.62 millimolar, and we'll produce twice as much, 5.24 milli. I've got writing these as molar, okay? So that's the carbonate hardness due to calcium. The next reaction is the carbonate hardness due to magnesium. So let's go back. Let's look at the bar chart. How much carbonate hardness due to magnesium do we have? No, remember, okay, carbonate hardness corresponds to my bicarbonate. Good one. We have 0. Look at my magnesium. All of my magnesium is associated with other anions. So it's associated with non-carbonate hardness, not with bicarbonate or carbonate hardness. So this is 0, and we don't need to worry about carbonate hardness due to magnesium. Does that make sense?
Dr. Masson?
Mm-hmm.
Does magnesium only add to carbonate hardness when the bicarbonate is greater than the calcium ion concentration?
Mm-hmm. So we had the situation, I'll draw it below. So if we had the situation below where, for instance, this, I'm going to make sure I'm using the consistent colors. So if this were my bicarbonate concentration, then notice here I have more bicarbonate than I have carbonate. So more bicarbonate than I have calcium. So I have, in this case, all of my calcium here would be associated with bicarbonate, and I would have magnesium also associated with bicarbonate. So in this case, I would have carbonate hardness due to magnesium. But in the situation that I've given you, we have a deficiency, essentially, of bicarbonate compared to our hardness. So for that reason, my carbonate due to magnesium is equal to 0. The next reaction I want to look at is my non-carbonate hardness due to calcium. And here the reaction is calcium, plus we're adding soda ash now. Now let's go back and look at the bar chart, how much non-carbonate hardness due to calcium do I have? Exactly, 12. Okay, it's the difference between the 274 and the 262. It's only this portion right here. 0.12 millimolar. I need 0.12 millimolar of soda ash, and I produce 0.12 millimolar of calcium carbonate. If you don't mind, let's just do, we've got one more reaction and it won't take very long to finish this. So the last one we have is non-carbonate hardness due to magnesium. So we have magnesium, and there we're reacting that with lime plus soda ash. And now going back to this, all of our magnesium is due to non-carbonate hardness. All of the magnesium is due to non-carbonate hardness. So we have here 1.28 millimolar. We need 1.28 millimolar, and we need 1.28 millimolar. So when we calculate the amount of lime that we needed 2.27, we needed 2.62. We didn't need any lime for the fourth reaction. We need 1.28 here. So we need 6.17 millimolar of lime. And soda ash, we need 0.12 millimolar plus 1.28. So we need 1.40 millimolar. So that gives us the amount of lime and the soda ash that we need. The last thing we need is you were told that the plant design flow is 4 times 10 to the 4 cubic meters per day. So if we take the concentration in moles per liter and we multiply that by the molecular weight, we actually add this as calcium oxide. So we'll multiply by this by grams per mole. We have to multiply this by 1,000 millimoles per mole. And we're going to multiply this by 4 times 10 to the 7 liters per day. We're at 1,000 grams per kilogram, and we need almost 1,400 kilograms per day. I'm going to leave you with that. I'm going to suggest, okay, between now and Friday, calculate the amount of soda ash that you would need, and we'll just do a quick check of that on Friday.